Let me show you how to do some calculations with solar energy. Everybody's seen these. These are photovoltaics, right? And that's the flashy thing, is to turn electricity or solar energy into electricity. But actually, the simplest thing is like in Israel, you can go out. I haven't seen this, but people told me this, right? What people do is they just get phone booths, old phone booths, and they stick big water tanks in them. And the sun beats down on that and just heats the water. This is called passive solar, right? Well, actually, I think it's active. Passive is just when it's like part of an architectural feature and it heats up your house, and like an Adobe house is passive solar. But people heat water to alarmingly high temperatures by just putting them in phone booths, water tanks in phone booths, and letting the sun just bake it. You can get a camp shower that just you lay a bag of water out in the sun and it'll heat up probably in about an hour or so and be warm enough to shower in. Here's some of the calculations. This is the basic formula. Is that intensity is power divided by area, right? Because this is watts per square meter, right? The intensity in watts per square meter. So power is intensity of the sunlight, right, times the area that it's hitting with, right? And that's called the solar constant. And this varies. You actually get more or less depending at the surface of the Earth, of course, depending on clouds, but also depending on sunspot level, and the sun heats up and cools down. It's not a perfect constant. So let's just look at some calculations here. One of the things you got to look at is the notion of, is your solar panel pointed at the light? So here's the light shining down at some angle like this, right? And the notion is this. What we have to do, we actually have to do like a cosine thing, just like we did with magnetic flux. This is now solar flux, right? And we have to do like a cosine between the angle of the sunlight and the angle of the area, remembering that areas have a vector that is perpendicular to them, right? So in this case, let's look at this example, right? The sun is shining. Here's our solar panel like that, right? The sun is shining at something that's 45 degrees above the horizon, right? So here's this solar panel here, right? Okay, and the sun is making a 52 degrees, sorry, angle above the horizon. And what that means is that here's the sun, and it's coming down like that, and this angle right there is 52 degrees, right? Okay, but remember that this solar panel has an area vector that points straight up. There's our area, right? So the real question here is, what's that angle right in there? Yeah, isn't it? Okay, so that angle in there is actually, what is it? I can't do this. It's like higher math. Is it 38 degrees? Right? That's actually going to be the angle between the area and the solar flux, right? I'm so paranoid here. I don't want to get it wrong. Everybody be laughing at me. Yeah, that's 90. Okay, so draw a careful picture, right? Okay, that's going to be our angle, and so we can figure this out. Let's see, we want to know what is the power is available for solar on the roof, right? Okay, so the power is going to be the area times the intensity, right? And then basically we have to put a cosine of the angle in there, right? Okay, so the area is 3.4 by 15.2, right? And then we have to do a cosine. Oh, we didn't put the intensity in there. Okay, I'll put it in there, right? Cosine of 38, and then I have to multiply the intensity. I forgot to do that, and the intensity is 1,020, right? And that's watts per square meter, right? Okay, so let's figure out the available power. So 3.4 times 15.2 times cos 38. I'm always paranoid, and then times 1,020. And I get 41538 watts. That's available. That's pretty much 42 kilowatts, right? It'd be 41.538 kilowatts of power, right? And then if the solar panels are 23% efficient, right, then we're going to get 23% of that, right? So I'm going to multiply by 0.23. And I'm going to get 9,553 0.9 watts, which I guess would be 9.6 kilowatts, right? Yeah. So just be careful about it. I guess the formula really is power is area intensity times area times the cosine of the angle between the area and the area vector being perpendicular to the surface and the sun's rays. Yay.